Welcome to video number 5. Today we're going to talk about the superposition theorem. Although it's an intimidating name, the superposition theorem is not really that complicated. And basically what superposition does is it allows us to analyze linear circuits with multiple sources in a relatively intuitive way. Now, there are other ways we could analyze linear circuits. We could use mesh analysis, nodal analysis, or loop analysis, but I think superposition is a more intuitive method than any of those. And we're going to use a little bit of theory from the preceding video that I did on ideal voltage and current sources. And in particular, I'm going to use the fact that the internal resistance of an ideal voltage source is 0 ohms. So keep that in mind as we work through this example. Okay, now what we've got here is a circuit with two sources, a 5-volt source labeled V1, a 10-volt source labeled V2. And what we want to do is determine the voltage at node A with respect to ground. That's labeled V sub A. It also happens to be the same as the voltage drop across R3. All right, superposition allows us to do this analysis in 2 steps. Step number 1, we leave V1 active and we deactivate V2. When we deactivate V2, we're just turning its terminal voltage down to 0 and leaving only its internal resistance of 0 ohms. So if I were to deactivate V2, we have 2K going straight to ground. Let's redraw the circuit to make that a little more clear. All right, again, deactivating source V2 allows us to draw this 2K in parallel with the 1K, R2 in parallel with R3. Now, we have 2 different formulas we can use to calculate the equivalent resistance of these 2 in parallel. We can use the product over the sum or the reciprocal of the sum of the reciprocals. Personally, I like this version better, but you can use either one. So applying this equation, R2 in parallel with R3 is 1 over 1,000 plus 1 over 2,000. That gives us an equivalent of 667 ohms for these 2 in parallel. Redrawing it over here for the sake of clarity, we end up with 5 volts driving 1K in series with 667. That is what we would call a voltage divider. This input voltage is divided between these 2 resistors. Without derivation, we can assume that V prime A, the response with V1 acting alone, is given by this formula called the voltage divider equation. Maybe in a future video I'll derive that, but for right now, if we want to know this voltage, we just take the input voltage times this resistor over the sum of the resistors. So that gives us 5 volts times 667 over 1,667, 2 volts. So this source acting alone gives us 2 volts at node A. Deactivating V1 and keeping V2 alive, we end up with this equivalent circuit. So V2 is driving these 2 in parallel through R2. R1 and R3 are both 1,000 ohms, so that's an easy one. 1,000 in a parallel with 1,000 is 500, but if you want to go through the formal equation, here it is. It gives you 500 ohms. Redrawing the circuit for clarity, here's what we've got. This is a voltage divider driven by 10 volts. We're interested in the drop on this resistor, so we put that one in the numerator. The sum of the resistors around the loop in the denominator times the applied voltage gives us 10 times 500 over 2,500 is, again, 2 volts. So source V2 acting alone would give us 2 volts at node A. We'll call that V prime prime A. Now, superposition tells us that V sub A is actually equal to V prime A plus V prime prime A, which is V sub A equals V prime A plus V prime prime A. And those were 2 volts and 2 volts. So we should get 4 volts at node A. And I don't know why I wrote A. That is 4 volts. Probably because it was node A. But, okay, that's all well and good, but let's verify this experimentally. All right, here I have our resistive circuit constructed with R1, R2, and R3, 1K, 2K, 1K. And I've thrown together a little power supply here that uses 2 9-volt batteries and a couple of voltage regulators to give me 5 volts and 10 volts. Here's my Astro AI digital multimeter. We'll set it for voltage, DC. We'll connect the black lead, the negative lead, to ground. And let's verify first that we've got 5 volts and 15 volts coming in. So let me connect my batteries up. All right, we should have 5 volts on this side. And we've got 5.016. Okay, close enough. And on this side, we should have 10. And we've got 9.99. Again, close enough, especially considering these are 5% tolerance resistors. That's pretty good. All through here. Okay, and then at this node, 3.9. Okay, that's pretty darn close to 4 volts. And again, using 5% tolerance resistors, that's not bad at all. So now we have a concrete demonstration that the superposition analysis we went through is actually valid. Now, if you're interested in more explanation of this or some problems to work out, or maybe even a schematic for this power supply, let me know in the comments. And that's it for today. I will see you next time.